So today we're going to talk about complex numbers in polar form. You've seen complex numbers before. What do you know about complex numbers? They're complex. What makes them complex? Complexity. This is kind of circular reasoning here. What's a complex number? What's that? Well, they could have a pi in them, but they definitely usually have something else. A square root of a negative number, which is usually written as a high. All right. So complex numbers, we might have something like 8 plus the square root of negative 9, which we would write as 8 plus 3i, because the square root of 9 is 3, and then the negative gives us the square root of negative 1. The square root of negative 1 we define to be I. So we've seen complex numbers, and well, at least you should have seen them back in Math 1412. All right, the first thing we're going to do today is we're going to graph complex numbers. We graph them on something that looks very much like the grid we're used to. On the x-axis, we're going to have the real part, and on the vertical axis, we're going to have the complex part. So on and so forth. So if I asked you to graph 2 plus 3i, where would 2 plus 3i be? Well, I start at the origin. I go over here to the 2, and then I go up to the 3i, right there. So we would put a dot right there. This would be 2 plus 3i. Instead of a comma, it's an addition sign. Correct. All right, so how about that point right there? What would you call that point? All right, so you would call it 0 minus 3i, and typically we would just call it minus 3i. But 0 minus 3i is not wrong. What about that point right there? Negative 2 plus 2i. And finally, how about a point right here just on this axis? Like that one. It would just be 4. That's correct. It would be 4 plus 0i. Typically, we would call that 4. So that's a little weird to have something 4 and put it on the x-axis, but that's the way it is. Think of the x-axis as just the real number line. So real numbers go here, imaginary numbers go up in here. All right, so the first thing we have today, and the problems we're going to be asked to do, sketch the set in the complex plane, where z is any complex number a plus bi, where a is less than or equal to 0 and b is bigger than 0. Alright, so here's my complex plane. What's it say about our complex numbers when I say a is less than or equal to 0? A is what again? A is the real part. So where is a less than or equal to 0? Over here, right? And then b has to be a positive number. So where is b a positive number? Basically, I'm giving you quadrant 2, except for this one little thing that has the equal to here, which means we include the top part of the axis. So to graph it, we would do that, and then we would shade this whole region. So we have the equal to on the A, which means we get the axis here, and then we shade everything in quadrant 2. All right, number 2, we have a fancy new symbol here. Z equals A plus BI, where 2 is less than or equal to, what would you call that? It looks like absolute value, but absolute value is only a thing with real numbers. Now we're dealing with complex numbers, less than or equal to 5. In terms of complex numbers, here's what this is. If I give you the point 2 plus 3i, its absolute z value is the length from the origin up to there. And this is called the modulus. Modulus, maybe, I don't know if I can spell it. It's called modulus. It's called the length. Sometimes called the norm. You'll hear all those words. So, if I give you a complex number like 2 plus 3i, how am I going to figure out how far it is from the origin up to there? I draw a triangle. This length is 2. This length is 3. So how do I find that length? Pythagorean theorem. All right. So for this problem, the modulus would be 2 squared plus 3 squared square root. So it would be the square root of 13. So in general, the modulus of a complex number is just the Pythagorean theorem. It's the length from the origin is the square root of a squared plus b squared. Alright, so back to this problem. I'm telling you I want all the complex numbers whose length is between 2 and 5. What the heck does that look like? Now, can you give me any old complex number in the whole wide world that has length 2? What'd you say? 2i would have length 2, wouldn't it? 2i would be right here. That would have length 2. Can you give me another complex number that has length 2? Negative 2i would have length 2. How about some numbers on the other axis that would have length 2? 2 and negative 2? Okay, so there's 4 complex numbers that have length 2. What would all the complex numbers that have length 2 look like? It would be a circle. So all the complex numbers with length 2 would be this circle. Like so. How about all the complex numbers that have length 5? What would that look like? A bigger circle. I didn't leave myself enough room, so I'm going to have to make a mess of my sheet here. But this would be length 5. Looks like so. So I'll just mark a few points here to show that this has length 5. That's 5i up there. So, what are all the numbers, all the complex numbers, whose length is in between 2 and 5? Like ones that have length 3 and 4, and ones that have length 2.5, and ones that have length pi. So how do I show that on my graph? I shade in the ring. So all the complex numbers who have length between 2 and 5. What's that? Yes, and I should shade the rings because we do have the equal to's. So I'm just going to, if I didn't want to shade the rings, I would draw them dotted to indicate that they're not shaded. So since I drew them solid this time, it does indicate that I want the equal to. So I might do that up here to indicate that I don't really want that axis. You would draw it dotted like so. Probably should have done that to indicate the difference. Questions on that? All right, the next thing it says, write the following in polar form. Well, that's the whole title of this section, polar form of complex numbers. I got extra ones, so I'm going to use a clean one here. So it looks nice. -3 minus I, where's that point? Our negative square root of 3 minus I, where is that point? Which quadrant? 3, because this would be negative square root of 3, -1. So it would be right about here. Negative square root of 3 minus I would be right about there. It says write it in polar form. What does that mean? Well, we did polar points a few sections ago, didn't we? So how do we write things using polar form? What do we need to know? R and theta. All right. To put this in polar form, I want exactly the same thing. So I want to know the R value. Except when we're dealing with complex numbers, we don't call it R. We just called it something different a minute ago. What did we call it? It's the absolute value. Absolute value. So R, instead of R, we're going to use the norm, the length of the complex number. So this complex number, it has length negative square root of 3 squared plus -1 squared square root. So that's 3 plus 1, that's 4. The square root of 4 is 2. So this length is 2. And then I need to know the angle. So I would need this angle. How do I find that angle? Call it theta. How did we find the angle when we were dealing with polar points before? If I knew, basically what I know here, this is the x and this is the y. X is negative square root of 3, y is -1. If I knew the x and the y, how did I find the angle back in section 8.1? We had a nice little formula. Tangent of theta was y over x. Correct. So to get the angle, we do tangent inverse. So tangent of theta in this case is going to be -1 over negative square root of 3. So tangent of theta is 1 over the square root of 3, which is a fancy way of saying square root of 3 over 3. So I look at my chart. That's one of the famous numbers I've memorized on my chart. What does that tell me theta is? Pi over pi over 6? 3. Pi over 3. One of those two. I agree. It's pi over 6. You're right the first time. Unfortunately, pi over 6 cannot possibly be the right answer, but it's close. What's wrong with pi over 6? That's in quadrant 1. I need the equivalent answer in quadrant number 3. So how do I take a quadrant 1 angle and move it to quadrant 3? I add pi. So it should be 7 pi over 6. All right, so here's the final answer. This number, written in polar form, it's going to be the length, which is 2, times cosine of the angle, cosine 7 pi over 6, plus I sine 7 pi over 6. And you just leave it. And why do I have 2 times cosine of the angle? Well, again, remember back from the previous section, this is r. What's r cosine theta? R cosine theta gives you the x number. And then this one would be r sine theta. R sine theta gives you the y number. And so notice the x number is the real part, and the y number is the one that has the I. So that's what you're going to do for these problems. You're going to find the length, and then you're going to find the angle, and it'll always be length, cosine theta, plus I sine theta. Okay, so this next one's a lot easier. If I give you the square root of 2, what's the length of the square root of 2? I'll draw you a picture. Here's the point, square root of 2. Remember, it's square root of 2 plus 0i. How far is it from the origin to the square root of 2? It's the square root of 2. It's its own distance. That's correct. Looking at the picture, what's the angle theta? The angle is 0. So to put this in polar form, it's square root of 2, that's the length, cosine 0, the angle is 0, plus I sine 0. So that one was a lot easier. All right, negative 5i, I think that's a pretty easy one too. Where's negative 5i if I graph it? Straight down, it's down here. Negative 5i. So what's the length? How far is it from the origin down to negative 5i? Not negative 5i, not 0. Not negative 5, but you're closer. Distances are always given as positive numbers, so it would be 5. All right. So if I had to do it using our formula, the length of negative 5i would be the square root of 0 squared plus negative 5 squared. Where did the 0 come from? Doesn't have an x. This is 0 minus 5i. So the length would be the square root of 25, which is 5. Length is always given as a positive number. So that would be 5. So negative 5i is 5 cosine. What's that angle? 3 pi over 2. 5 cosine 3 pi over 2 plus I sine 3 pi over 2. So when you have just a real number, writing it in polar form should be nice and simple. Your angle is going to be either 0 or pi, if it's a negative. If you have just a complex number with no real part, then it's just the length, which is the number out front, and then it's either going to be cosine pi over 2 or cosine 3 pi over 2, depending on if it's up or down. Those should be easy. D is not so easy, unfortunately. So for D, the first thing we have to do is find the length. The length is the square root of 4 squared plus 3 squared, which turns out to be a nice number. Square root of 25. That's 5. That's nice. That doesn't always happen. And then we have to find the angle. So theta is tangent inverse of y over x. So that's 3 over 4. Is that one of the ones we've memorized? No. So what do? We type it into our calculator and we get a decimal. What did your calculator say? 0.6435. So we'll call it 0.644. We'll round to 3 decimal places. Now be careful, is this in the right quadrant? Like remember back up here, originally we got pi over 6, but then we said that's not possibly the right answer. Is 0.644 in the right quadrant? Yeah, because this original point, which quadrant is it in? It's in quadrant 1, and when I do tan inverse, I either get quadrant 1 or 4. So if this is a positive number, it's quadrant 1. So this is the right quadrant. If it wasn't the right quadrant, I might have to add a pi to it, but it's the right quadrant. So our answer would be 4 plus 3i. In polar form is 4 cosine 0.644. I said 4 and I wrote 5?
Yeah.
All right.
That's how everybody looks up. Like, what?
And I was looking down, so I didn't see that you looked up. Plus I sine 0.644. Questions on that one? Pretty straightforward. Okay, good. Well, and it's almost exactly what we did back in section 8.1. So it's really kind of a repeat of what we did in section 8.1. Now, the big question you should be asking is, why do we write complex numbers in polar form? And there's a reason. It has to do with the backside. Determine the product and quotient of those numbers. Oh no, looks awful, doesn't it? Good news is it isn't. So I'm going to give you z1 times cosine u plus I sine u, and I'm going to multiply by z2 cosine v plus I sine v. And we're going to come up with a nice formula for how to multiply two complex numbers in polar form. Well, the first thing I'm going to do is I'm going to switch the order, and I'm going to take this z2 and I'm going to move it over here. So I multiply the z1 and the z2. So I multiply those two things together. And then I have this thing, this parenthesis thing, times that parenthesis thing. How would you multiply two parenthesis things like that together? You would do FOIL, just like you always do. All right, so when I multiply this and this, I'm going to have a big mess, but it's going to be okay in the end, you watch. I'm going to have cosine u, cosine v. Cosine u, cosine v. On the outside, I'm going to have an I, and I'm going to write it this way for a reason, and you'll see why in a minute. Sine v cosine u. I chose to put the sine one first because I wanted to. On the inside, I have another one that has an I. It has a sine u and a cosine v. And then finally on the last ones, I have plus I squared sine u sine v. I ran out of room, so I wrote it tiny there. But that says sine u sine v. What's I squared? I squared isn't 1. I squared is negative 1. Okay? So, if I replace this by a negative 1, this one doesn't have any more i's in it. So I'm going to put this one next to that one, because those are not going to have any i's in them. And then these two both have an I, and I'm going to factor that I out. All right, so I have length of z1, length of z2, times, this one's going to be cosine u cosine v This I squared was a negative, so that's minus sine u sine v. So that's these two that I put a square bracket under. These two, I'm going to factor the I out, so plus I. This one has sine v cosine u plus sine u cosine v. Alright, we're almost there. I know it's gotten ugly looking. It's about to get pretty. Well, as pretty as a math formula gets. This should be something you recognize. What happens when you go cosine cosine minus sine sine? That's one of our formulas. Which formula is that? Oh, we don't remember. See, this is the downside of not forcing you to memorize all these formulas. This one happens to be cosine of u plus v. Add the two angles. Plus, then we have this I, and then we have another famous one. This one goes sine cosine, and then it switches. So it has sine v cosine u, and then it switches sine u cosine v. That's another one of our famous formulas. Which one's that one? Sine of, close, sine of u plus v. The cosine one, when you have a plus here, you get a minus there. The sine one, when you have a plus here, you get a plus there. Sine of u plus v. In other words, look how easy this is. To multiply two complex numbers that are written in polar form. You multiply the lengths that are out front, and then what do you do with the angles? All you have to do is add the angles. Alright. So that's it. So this problem here looks really hard. It says multiply these two things together. It turns out it's really easy. To multiply these two numbers together, I multiply the lengths. So the length of the first one is square root of 2. The length of the second one is 2 square roots of 2. I multiply those two things together. What's 2 square roots of 2 times the square root of 2? It's 4. Because the square root of 2 times the square root of 2 is 2. And then this other 2 makes a 4. So I multiply these numbers together. That's a 4. And then I'm going to have cosine. And what do I do with the angles? I just add the angles. So I'm going to have 5 pi over 3 plus 3 pi over 2. And in just a minute I'll simplify that. Plus I sine, I add the angles. 5 pi over 3 plus 3 pi over 2. So my final answer is 4 times cosine. Alright, what's 5 pi over 3 plus 3 pi over 2? What's the easy way to do that? Do you agree that the answer is going to have a pi in it at the end? Yeah. So forget about the pi for a minute. What's 5/3 plus 3/2? Well, maybe I don't know right off the top of my head, but I know my calculator is really good at adding fractions. So I grab my calculator and I do 5/3 plus 3/2. My calculator says 5/3 plus 3/2 is 19 over 6. So what's 5 pi over 3 plus 3 pi over 2? 19 pi over 6. You can use your calculator to add those fractions. Just ignore the pi and put the pi back at the end. 19 pi over 6 plus I sine 19 pi over 6. That's it. So to multiply two complex numbers in polar form, you multiply the things out front, and then you add the angles. That's why we write them in complex form. Multiplying them in complex form is very, very easy. Conversely, it asks us to find the quotient. Oh no, quotient means divide. How do you think you divide two complex numbers? You divide the numbers out front, and then what do you do with the angles? You subtract them. So, I didn't leave myself a whole lot of room, so I'll squeeze it up at the top here. Z1 divided by Z2 would be, I have to take the square root of 2 and divide it by 2 square roots of 2. What's square root of 2 divided by 2 square roots of 2? 2? Not 1, not 2. Square root of 2 divided by 2 square roots of 2. It's 1/2 when you do it correctly. The square root of 2 is reduced out. And you're left with a 2 down on bottom. Yeah, that wasn't supposed to be hard. You guys made that a lot harder than it was. That's a 1/2 when you divide those. And then you're going to have cosine of 5 pi over 3 minus 3 pi over 2 plus I sine 5 pi over 3 minus 3 pi over 2. Final answer has a 1/2 cosine. Again, you grab your calculator. What's 5 pi over 3 minus 3 pi over 2? Again, forget about the pi's for a minute. Do 5 over 3 minus 3/2. And you get 1/6. So it's just going to be pi over 6. And then plus I sine pi over 6. Questions on that? Correct. The answer will always have a plus, never a minus. But what happens sometimes, it depends on where this angle ends up. If this angle ends up in quadrant 3 or 4, then the sign thing is a negative, so this would be a minus in the end if you plotted the point. But you always put a plus, and then it depends on that angle where it comes out to be. Okay, so let's say I gave you Z1 is square root of 2 minus square root of 2i, and Z2 is 1 minus I. And I asked you to multiply them, divide them, and then take 1 divided by Z1. What would you do? Cry. No, crying doesn't help. I've mentioned that before. Just, it gets stains on your paper, makes it hard for the teacher to read it. What else could you do? Except the last one, they were written in polar form, weren't they? Are these in polar form? Well, they're currently in rectangular form. I would write them first in polar form and then do exactly what we did a minute ago. So I think I'm going to need some more room here. I'm going to just grab a sheet of paper. I don't think there's going to be enough space on that to do everything we need to do. Z1 is square root of 2 minus square root of 2i, and Z2 is 1 minus I. Okay, so to convert those into polar form, first I have to find the length. So the length of Z1 is going to be, I take the square root of 2 and I square it. I take negative square root of 2, I square it. And then I take the square root of that whole thing. And I think I get 2. Because this is 2, that's 2, 2 plus 2 is 4, square root of 4 is 2. And then I need to find the angle. So theta is tangent inverse of the y, which is negative square root of 2, divided by the x, which is square root of 2. So theta is tangent inverse of negative 1. What's the tangent inverse of negative 1? It is one that we remember. Negative pi over 4 is the correct answer. Negative pi over 4. Because the tangent inverse of 1 is pi over 4. Since it's negative pi over 4. But be careful. Is this in the right quadrant? Think of the graph. Where's this original point? Which quadrant is it in? 1, 2, 3, 4. It's in 4 because it's over and down. Is that in the right quadrant? Yes, it is. Okay. Again, watch out for that. If this point were originally in quadrant 2, we would get this same answer. We would get negative pi over 4. We would have to add pi to it. Always make sure you're in the right quadrants. All right, so Z1, I can write Z1 as 2 cosine negative pi over 4 plus I sine negative pi over 4. There's Z1. Go ahead.
So it's only
Correct. It's
all.
all
It's just regular not absolute.
correct. So when you're figuring out the length, we use the symbol that looks like absolute value, but in this case, this symbol doesn't really mean absolute value. In some books, I've seen this notation, which I like better. They put double bars there to indicate length. So that kind of looks better, actually, to me. In fact, we'll use that symbol later on when we talk about vectors. We'll talk about vectors. The length of the vector, we'll use that symbol. So this is not really absolute value, it's length. And length is always given as a positive number.
Okay, so when we're writing that, if we do the double bars,
That's okay with me, absolutely. All right, now we need to do the exact same thing with Z2. All right, so the length of Z2 is the square root of 1 squared plus negative 1 squared. That's square root of 2. And then I'm going to use a different, I don't want to use theta again because I already used theta, so I'll use alpha. Alpha will be the tangent inverse, although it's not going to make a difference now that I look at it, of negative 1 over 1. That's the tangent inverse of negative 1, which is still negative pi over 4. And again, I'm still in the correct quadrant because this original point was in quadrant 4. Negative pi over 4 is in quadrant 4. So again, check your quadrants on that. All right, so Z2 in polar form is square root of 2 times cosine negative pi over 4 plus I sine negative pi over 4. Now I'm ready to answer the questions. Z1 times Z2. I multiply the numbers out front. So I multiply the 2 and the square root of 2. Well, that's easy enough to do. That's 2 square roots of 2. Cosine of, I add my angles. What's negative pi over 4 plus negative pi over 4? Negative pi over 2. Because it already has common denominators, so I add the tops and I can simplify. So that's negative pi over 2 plus I sine negative pi over 2. Now, it might be nice, since our original problems started in rectangular form, it might be nice, if it's convenient, I suppose, to write this in rectangular form. but it's not so bad. What's the cosine of negative pi over 2? It's 0. And what's the sine of negative pi over 2? Not 1, negative 1 because it's straight down. All right, so this is, in rectangular form, 2 square roots of 2 times 0 minus I. In other words, it's negative 2 square roots of 2 I, putting it back into rectangular form. Read the directions carefully on MyLab. I'm not sure what, or not MyLab, you guys use WebAssign. Read the directions carefully on WebAssign. I don't know if it forces you to go back to rectangular form. It might just accept polar form, and you might be able to just type this one. But it's kind of nice since we started in rectangular to end in rectangular. All right, now let's divide them. Z1 divided by Z2. Again, I'm going to divide the numbers that are in front. So that's going to be 2 divided by square root of 2. And then I subtract my angles. So I'm going to have cosine of what's negative pi over 4 minus negative pi over 4? 0. Cosine 0 plus I sine 0. And again, I think I'll convert back to rectangular form. That's going to be 2 over the square root of 2. What's the cosine of 0? Alright, what's the sine of 0? The very first thing on your chart is in the upper left-hand corner. Sine of 0 is 0. Sine of 0 is 0. And cosine of 0 is 1. So this is 1 plus 0, that's just 1. So the final answer in rectangular form is 2 over the square root of 2. Cosine of 0 is 1, sine of 0 is 0. The last thing it asks us to do, this is a little different, it asks us to take 1 divided by Z1. So how do I take a regular old number like 1 and divide it by a complex number? Well, I'm going to take 1 and I'm going to write it in polar form. What's 1 in polar form? What's its length? How long is 1? It's 1. That's correct. What's its angle? 0. So I could write this as 1 times cosine 0, 0, that's a 0, plus I sine 0. And then I got to divide by Z1. So I do the exact same thing. I divide the numbers. I have the 1 divided by the 2. So that's 1/2. Cosine, I subtract my angles. What's 0 minus negative pi over 4? 0 minus negative pi over 4 is positive pi over 4. 0 minus a negative, 2 negatives, plus I sine pi over 4. So taking a complex number on bottom really isn't a big deal because you're just going to have your angle to be 0 if you're dealing with a real number. Again, I might put this back into rectangular form. This is 1/2 times cosine of pi over 4. Square root of 2 over 2 plus I square root of 2 over 2. So as a final answer, I might write this as square root of 2 over 4 plus I square root of 2 over 4. Again, check the directions on WebAssign. I don't know what they want, but it seems to make sense to me. You start in rectangular form, you end in rectangular form. All right, last thing, powers. Let's stick with this number for a minute here. Z1 was square root of 2 minus square root of 2i. which we learned was 2 cosine negative pi over 4 plus I sine negative pi over 4. What if I asked you to square Z1? How would you square a complex number? Well, what does squaring mean to do? Multiply it by itself. So that would be Z1 times Z1. So how do I take this and multiply it by itself? Well, I take the number up front and I multiply it by itself. So I take 2 times 2. That's 4. And then what do I do with the angle? I add it to itself. So I'm going to have negative pi over 4 plus negative pi over 4. So that's going to be cosine plus negative pi over 4 plus negative pi over 4. Negative pi over 2. Plus I sine negative pi over 2. What if I wanted to take that number and I wanted to cube it? I could multiply that by what I just did. So I would multiply the 4 times the 2. 4 times 2 gives 8, which notice that happens to be the 2 cubed, the original number cubed. So I'd have 8. Cosine of, I would add my angles. So I'd have negative pi over 4 plus negative pi over 2. But remember, negative pi over 2 was negative pi over 4 and negative pi over 4 again. So I would have negative pi over 4, negative pi over 4, negative pi over 4. What's negative pi over 4 plus negative pi over 4 plus negative pi over 4? Negative 3 pi over 4. Plus I sine negative 3 pi over 4. Alright, well I'm going to go crazy then. What if I wanted to take my number and raise it to the 10th power? What number would I have out front? And how did you get 1024? And what did you type into your calculator? 2 to the 10th. I would do 2 times 2 times 2 times 2 10 times. So I would have 2 to the 10th out front. Cosine of what angle? And you don't have to give it to me reduced. In fact, I would prefer it not reduced. Make the point. Well, if I'm multiplying 10 times, what am I going to do with the angle 10 times? I'm going to add it together 10 times, aren't I? So I'm going to have minus pi over 4 plus minus pi over 4 plus minus pi over 4 10 times. So what do you get when you take minus pi over 4 and you add it up 10 times? Negative 10 pi over 4 plus I sine negative 10 pi over 4. And of course I could reduce that, but I wanted to write it as negative 10 pi over 4 to emphasize where I was getting it. Negative pi over 4 plus 9. Okay. So 2 to the 10th, which I could type into my calculator, I suppose. What was it, 1024? 1024. Cosine of negative 5 pi over 2 plus I sine negative 5 pi over 2. In other words, doing exponents in polar form is very, very, very easy. If I have z equals, z1 equals, let's say it's 4 cosine pi over 3 plus I sine pi over 3. And I want to do z1 cubed. All I have to do is cube the number out front. So that's 4 cubed. Cosine of, what's my angle going to be? pi over 3 plus pi over 3 plus pi over 3. That's 3 times pi over 3. So to do a power, you do the power of the first number. The angle, you multiply by the power. So it's going to be cosine pi plus I sine pi. And that's it. Exponents are very, very easy in polar form. All right, the last thing that we don't have time to talk about today, so hopefully I will remember Monday, because Friday we have a test, right? And then we have a whole week off for break, so hopefully when we get back from break, I will remember to tell you we need to talk about how you do square roots and cube roots and fourth roots of complex numbers. That's the only thing left in this section.